My name is Nancy Brickhouse. It's on, yes. Due to an unexpected circumstance, Charles Alcock is unable to be here today and has asked me to serve as host for this colloquium. It's become a tradition at the CFA colloquium to include a historical or philosophical presentation. And keeping to this tradition, it's my great pleasure today to introduce our own Owen Gingerich. Owen first came to the Harvard College Observatory in 1949 as an undergraduate assistant in the summer to Harlow Shapley, who was the HCO director at the time. He was a student at Goshen College where he got his undergraduate degree, and then he came to Harvard to get his PhD in astronomy. He is currently Professor Emeritus of Astronomy and the History of Science at Harvard and Senior Astronomer Emeritus at Smithsonian Astrophysical Observatory. His book on his adventures studying Copernicus through first and second print editions, entitled The Book Nobody Read, is now available in 14 foreign editions. Today he will tell us about what he considers to be the greatest myth in the history of astronomy.
Thank you very much. One of the exciting things about doing science is it's very much like a detective story. You make your observations, you find those as clues that then require some sort of solution, some coherent view that puts them all together. And history of science is somewhat like that too. The detective work more typically will be looking for clues not in the sky itself, but perhaps what people saw in the sky in times past. Here is one kind of a source for that, and I'm going to show you this book later, but I just wanted you to see how big it is. So, never mind. Now that you've got that idea, we're ready to march on. I'm sure most of you have heard it said at some point, well, perhaps my theory has too many epicycles in it. And even if you don't have any idea what an epicycle is, you get the big picture. It's the idea that somehow your theory is too complicated. It has too many free variables in it or whatever, and you maybe should back off on that a little. King Alfonso of Spain had his astronomers at work to make new tables back in the 13th century. And somehow a rumor got started that he, looking over the shoulders of his astronomers, said that if he had been present at creation, he could have given the good Lord some hints. The idea somehow being that it was too complicated. And that story gets, in a certain sense, propagated, and the earliest place I have been able to find it is in the writings of John Herschel, the son of William Herschel, an astronomer in his own right and a great pioneer in photography. Astronomy, therefore, continued for ages a science of mere record. Hence arose an unwieldy mass of hypothetical motions of sun, moon, and the planets, in circles whose centers were carried round in other circles, and these again in others without end, cycle on epicycle, orb on orb, till at length, as observation grew more exact and fresh epicycles were continually added, the absurdity of so cumbrous a mechanism became too palpable to be borne. That's a quotation, by the way, from John Milton, who was considerably earlier than John Herschel. I've always thought that perhaps the idea of epicycles on epicycles arose from the from the Fourier series, that you could keep adding more and more trigonometric terms to get any desired level of accuracy. And that was already in the books when John Herschel wrote this in 1830, so there might have been some connection. But the story carries on. In Thomas Kuhn's The Copernican Revolution, he writes, to increase the accuracy or simplicity of the planetary theory, Ptolemy's successors added epicycles to epicycles and eccentrics to eccentrics, exploiting all the immense versatility of the fundamental Ptolemaic technique. Systems employing a half dozen to a dozen minor epicycles were not uncommon in antiquity and the Renaissance, for by an appropriate choice of the size and speed of minor epicycles, almost any sort of small irregularity could be explained away. Both what Tom Kuhn says here and what John Herschel said back in 1830 are completely wrong. And I'd like to explain to you why that is the case, but that's not the greatest myth in the history of astronomy. Let's just think a bit about how you might want to make a simple approximation of the planetary motion. Well, you might want to start out with two circles. One circle essentially representing the orbit of the Earth, the other circle representing the orbit of the planet. And so here you can see two circular motions, and you will notice that the Earth is not placed in the center of this large carrying circle. And that is essential because the planet's motions in the sky are not uniform in terms of speed in the circle. So essentially, if you divide the sky here, then if the motion is uniform in this circle, or maybe I should make it go the other way, but then this part would be seen in 1/4 of the sky as seen from the Earth, but the mechanism would go much faster here because it's shorter distance. And over here, it's going to appear to go much more slowly, even though on the circle itself, it's moving at a uniform speed. Now, in order to make a simple table to show this, you would want to have some trigonometric relationship between angles going around this point and angles going around the center. So you might want to make, let us say, a 180 entry table, one for each degree as you go around there. Why 180? Because there's symmetry. You don't have to do it all 360. Now, here's the epicycle. So you also need to have 180 positions going around in the epicycle. But now there's a problem. You're looking at the epicycle here from a rather great distance. But when the epicycle is up here, the effect of the motion in the epicycle is different. So clearly, you're going to need a 180 by 180, a double entry table, in order to make it easy to get these motions put together for a prediction. But now suppose you wanted to get a little bit of refinement to this. And so you have an epicycle on an epicycle. Okay, here's another 180 possibilities. But wait a minute. It's going to look very different when it's here compared to when it would be, let's say, over on the other side. So that means 180 by 180 by 180. It's getting pretty complicated. Too complicated for any mathematicians in the Middle Ages to even think of coping with this. Well, let's just take a look at here's a quotation. We'll get to the rest of the quotation later on, coming from John Barrow's recent book of the universes. Okay, now sure. not true because you have to have a variable speed. I'll get to that in a little bit. But no system would work if you had the Earth in the middle of the big circle. Okay, so here we go. Here's a set of tables, the Alphonsine tables. These are the ones that were made at the behest of Alfonso in Spain, excepting that the tables that were made in Spain no longer seem to exist. This is the version that came some few decades later in Paris. Now, let's look at how it works. You will see that it counts down here, gets to 30 degrees, and it comes down here, and it gets you to 60 degrees. It says 1, 0. This is in the sexagesimal system, so that the 1 means that it's counted up to 60. Now, you have a column that comes down here, and it is called the equation of the center, and that is the effect of doing it in the big deferent. The epicycle is sitting over here. Well, now that's rather interesting, because rather than having a 180 by 180 table, you've got two linear tables, counting down, and so this is part of Ptolemy's great ingenuity. He found a way that you could make small corrections to the epicycle. That's what the other columns are for. And so you can get away with it all with just one epicycle treated in this ingenious way. Okay, so that means we're up to 1320, and it's still the single epicycle of Ptolemy's system. Let's march on just a little bit further. Oh, I was supposed to do this so you could see the numbers. All right, this is done by Regiomontanus, the leading mathematician and astronomer of the 15th century. So he was also a printer. He printed a basic set of them, but this is the second edition of the tables. And so, just to make sure, last week I took my program that can calculate these things by the Alphonsine method, and it hits within a minute or two on all these entries. So there's no further progress in adding little doodahs, little epicycles on epicycles, right up to the time when Copernicus was a youngster. So here we have something very strange. It's almost enough to blast the whole notion of epicycles on epicycles, because the state of the art here doesn't show anything of the kind. However, some of you are undoubtedly thinking ahead to Kepler and to the law of areas. And you're wondering how astronomy could be done with any accuracy before the time of Kepler if people didn't know about the law of areas. In fact, if you didn't do something about the law of areas, you would not have any system worth taking seriously. It's pretty amazing, though, what you could do with very rough observations. And what I'm showing you here is the type of information we can get from the Babylonian clay tablets. They had diary texts in which they would set it up for a particular month, and the months are actually moons. They are when you get the moon at the new moon. Now, the new moon is not as you would find it in the nautical almanac today, when the moon is in conjunction and invisible. It counts when the moon is seen as a first crescent. Many years ago, I taught at the American University of Beirut. And in the first week I was there, I got a call from the registrar asking when was the new moon in April of the next year. And I had no idea why he wanted this information. So I looked it up in the almanac and gave it to him. Well, he wanted to know when Ramadan began. And that depends not on the conjunction, but on the sighting of the crescent. And of course, the catalog of the university was wrong, and he never asked me again. I guess he thought that the university had just hired the world's most incompetent astronomer. Any rate, this chart is set up for minus 600, and this is the zodiacal sign in which Mars is found during each successive month, and you can see that some years you have a 13th new moon. We can see a little bit better what's happening here if we mark the places where it goes into retrograde. And you can see that here it's in Pisces, it goes into Aquarius and then goes back into Pisces again. And so each of these rectangles show you a time when the planet is in retrogression. But there's something else you can see from this, and let me instead mark the two times when the planet is going slowest in the sky and going faster. And you can see that in Capricorn it is typically for 1 month only, and 180 degrees away from it in Cancer, it's moving much slower here, and therefore tends to stay in that sign for 2 months. So from this relatively crude information, if you have it, let us say, for 32 years, so that the retrogrades all average out, you can get a very accurate idea of how much faster the planet goes in one part of the sky compared to the other. And the Babylonians were therefore able to set up an arithmetic way of predicting the positions of the planets. They did not try to predict just for any day you wanted to find out where the planet was, but they wanted to know when and where the retrogression would begin and when it would stop, and things like that. A big change took place when Ptolemy came on the scene, and Ptolemy now put it into a geometrical structure, which was the first time that this really happened in any detail, and for the first time it made it possible to predict the position of the planets for any specified day that you wanted to do it. Now, you need to know something else about the system, because though it worked okay for the sun to have the sun moving in a uniform rate, the sun doesn't need an epicycle, it doesn't go backwards, no retrograde, but for the planets, Mars, let us say, you could not make it work unless you moved the spot of uniform motion over here, and because you need to preserve this eccentricity, you then have to move the Earth over to here so that you have the same total eccentricity when you count both ways, but it is known as halving the eccentricity, which was then what Kepler did for the Sun, but it was already done for you by Ptolemy, having this uniform motion about this spot. So this is now the way Ptolemy has set it up. And let's just look at, here you can see the equant in this Latin copy of the Almagest, the copy owned by Michael Meslin, Kepler's teacher. You can see that you have the uniform motion going around the equant point So it moves through this 90 degrees here, but as seen from the Earth, it is moving relatively slowly in the sky, and over here it will go much faster in appearance as it goes around, because here, when it moves 90 degrees, it's going to have to go a much greater distance, so it's going to go a lot faster over there. Okay. Let's just think about what you have to do in order to set up the system. You need a certain number of parameters, and here you can see some of them. You need to get the eccentricity of the orbit, and of course that automatically means you know the distance to the equant, because those two are just set identically the same in the model. Then you have up here, you have to get the angle for this line of apsides, as it's called. You now need to know the period for getting around here, and also the epoch. You need to have a starting point, where it is on a particular date. Now, when you add on the epicycle, you now have to get the period in the epicycle and also the time to get that set. This, it turns out, for the superior planets, is very much related to the solar theory. So you get that from what you know about the sun, and for each planet then, there are just these 4 parameters that you need to establish. And therefore, Ptolemy is going to need 4 observations for each planet. You don't want to have 5 observations, because then you would have contradictions because of observational error. So let's watch out about that. Okay, so these are the predictions made from his theory, and it's compared with modern numbers. You'll notice, among other things, that there seems to be an error here of about -1 degree, setting it down like that. That's because Ptolemy's coordinate system had a glitch in where it started. So we don't worry about that. It's just too bad that he didn't get that number right, because it meant he didn't have the rate of precession right. But apart from that, you see that he's got 4 observations here of Saturn, and they all fit nicely on the error curve. Well, I guess you would expect that, because he's feeding those observations in, and the answer comes out that way. But here is a very subtle clue. We notice that for Mars, the observations seem to be much worse than for the other 2. But yet, if you're an observational astronomer looking at the positions of the planets, Mars is not moving fast enough to make that kind of an error. So something funny is going on here. I would suggest that Ptolemy must have had a great reservoir of observations at his disposal there in the great library in Alexandria, material that was coming in from the Babylonian astronomy for many centuries. And so Ptolemy was able to select very precisely observations that were in geometrically strong positions for determining the parameters. But not only that, he has enough observations that he can tinker with it and see where the stability is in the orbits. And now, trusting his theory, he can correct for observational error, because he would not want to have results, numbers in his Almagest that were not good, serious observations. So here's a method to figure out how much observational error there is. You can adjust them, but Mars is particularly intractable in its process because it has considerable eccentricity, much more than Venus or Jupiter or Saturn, and also it comes pretty close to the Earth. So there's trouble there, but it is a remarkably stable system. It's going to run for centuries without getting very seriously out of whack. Now, some of you are worrying about the fact that we don't have an ellipse in this system. And you know that Kepler has made this great achievement in finding the ellipse. So I thought you should just get a little bit educated here about the nature of this. This is showing with the eccentricity for Mars, and it's 10%. And now we can see an ellipse drawn to exactly the same scale. Here's the comparison. So you've been misled by all these elementary astronomy textbooks which talk about Kepler's laws and show you a big egg-shaped ellipse. But the ellipticity goes by the eccentricity squared, half of it. So if you have a 10% eccentricity, the amount that it bends in is 0.5%, which is barely visible to you here. So for this kind of rough work, we don't have to worry at all about whether we have an ellipse or not. Now here comes Copernicus, and the interesting thing is he can't make any observations that show for sure that it has to be heliocentric as opposed to geocentric. For Copernicus, what he's coming up with is a wonderful aesthetic idea, because as soon as he arranges the planets in a heliocentric arrangement, something wonderful happens. Mercury, the fastest moving planet, falls automatically closest to the Sun. Jupiter and Saturn fall out here at the edges. And these, by the way, are not orbits. These are shells defining the region where the eccentricity and so on takes place. So here in this shell you get the moon going around the Earth. Here's a space for putting the mechanism of Venus and for Mercury. The woodcutter for this diagram made a mistake. He put Mars outside there, and it should be put in the shell, which is right here. It's correct on his original manuscript, but it got botched up somehow at the printing office. So this could very well lead you to suppose that, in fact, the orbits are circular, centered on the Earth or centered on the Sun. But it's not so. You have to have the eccentricity. So here are the tables made from the Copernican system, called the Prutenic tables, and they're named partly after Prussia, where the area where Copernicus is from, but also for the Protestant Duke of the Prussian territories, outside of the Catholic country where Copernicus is. Let's just have a look at the tables. And you will notice how close they are to the tables, the Alphonsine tables. First of all, you have the columns which are for the motion of the planet's circle, and then the Earth's circle is inside. As it goes around, you're looking at the other, the planet in its orbit from two different points of view. It's like your two eyes. It's parallax. And so that's called the parallax of the orbit. And so you use this column, and then you make the little adjustments just as you did in the Alphonsine table. It's remarkable how similar it is. There's not a hint for somebody using this that he's using a heliocentric system. So you can be absolutely convinced that the Earth is standing still and none of this ridiculous business of the Earth spinning around like that. I mean, if the Earth's spinning around every 24 hours, why don't people just fly off into space? And as Schroner says, if it's doing that, it's going to be so much harder walking west than walking east. So you could use the newest cookbook, the recipe book, for making the calculations without worrying yourself at all about what's in the middle. Okay. I got into some of this by a couple of book dealers in London who got a copy, a manuscript copy, of the Bianchini tables, which were done when Copernicus was a youngster. And they wanted to know what was different and what was special about these tables. So I had to do some research in the literature about this, and what I found was it was just the arrangement of the tables. They were expanded in some ways to simply make the calculation a little bit easier. But the parameters, the underlying parameters, were still the same, and therefore there were no extra epicycles there. It was just redoing it. And as I started to think, I realized that all during the Islamic period, there were many zijas, as they were called, which were books of tables coming out. And essentially, these were rearrangements of the material to make the computing easier. Here, for example, is one very popular set, which came up through Spain and populated libraries in Europe, called the Toledan tables. And you'll notice, by the way, that it's a little bit harder to do the calculations if you have to do them with Roman numerals. So if you're looking in a manuscript library in Europe and you ask to see the astronomical tables, you can immediately know which ones are the Toledan tables and which ones are the Alphonsine tables simply by the way the numbers are put. In fact, it was the Alphonsine tables that helped introduce the number system that we now use into Europe. It was the very important avenue by which that simplification came. Now let's just look at how accurately this works. Here you can see the predictions from the Alphonsine tables compared with modern calculations as to where the planet Mars really was. And you will see that here in 1595 there came a 95, that doesn't seem quite right, but anyway, it's sometime along there, this major lift. I call it the Martian catastrophe because it goes off, and it goes off when Mars is at an opposition, so it's at its brightest, it's shining all night long, and it's 4 or 5 degrees off of the tables. The question is, did anybody notice? And it's very, very hard to find a place where there is some problem like this. I've asked my colleagues doing Islamic astronomy to tell me where there are observations, and they are very hard to come by. I noticed last week that in 1804, quite a few observations from Ibn Yunus, who worked in Cairo and who may very well be the greatest astronomer of the Islamic period. There are in this wonderful publication, it's a series, and amazingly Harvard doesn't have it in the library. A They don't even have an electronic copy of it. But good old Google, I found it, the whole thing. It's amazing what you can do these days. So I fetched out the 22 observations of Mars as it was in conjunction with these planets or the star Regulus, and put them through the computer and found that none of those observations hit one of the times when Mars was so radically off on the tables. I was rather amazed to discover that I'm a co-author of one of the three publications on these Islamic observations. There were two of Mars with Regulus, and that's kind of interesting. I'll come back to that in a moment. Here, by Yahya al-Maghridi, there are dates of observations, but not the observations themselves. Nevertheless, it was possible to take his three observations of Mars and see that he was dead on for the opposition. That is to say, when Mars was exactly opposite the Sun. And that, by the way, is a hard thing to know, because you can't observe the Sun and Mars simultaneously. And there's no coordinate system sitting there in the sky to tell you whether it's matching 180 degrees from where your tables say the Sun should be. But there it was, observations not given, but the dates were right on, but not one of those times when Mars was so violently wrong. Okay, so here's the book that I held up at the beginning. It was done in 1666 in an attempt to show all of the numerical observations of the planets, Sun, and Moon. And in 1666, they knew nothing of those clay tablets in Babylon, and they knew very little of what the Islamic astronomy was about. So all of the observations that he could find prior to Tycho Brahe are there in that front section of the book. These are the observations made by Tycho Brahe. And then these are the observations made in the following 30 years after his death. So I think this just has to give you an incredible admiration for what Tycho Brahe was able to accomplish. For the first time, there were enough observations that it would be really possible to check out how accurate the Ptolemaic tables were. And sure enough, because Tycho observed so regularly, he hit the time in 1593 when everything went berserk. It was the great Martian catastrophe. And you can see that the Alphonsine tables were 5 degrees off, and the Copernican tables were off in the other direction by 4 degrees. So there is a problem there, and I suspect that maybe the reason Tycho asked Kepler, when he showed up as an apprentice, to work on Mars was knowing that there was something wrong about the way Mars was working. I wondered, because Kepler knew that it happened again in 1625, so I could get the 32-year period of this, if I could go back and find another observation that would be 32 or 64 or 96 years earlier. And sure enough, I found one of them by Regiomontanus. Here is Regiomontanus sitting alongside the armillary sphere and alongside Ptolemy. That's not King Alfonso. There were a whole bunch of kings in Egypt called the Ptolemies. So during the Middle Ages, it got kind of mixed up as to whether the astronomer was one of the royal family, but apparently not. Here I've marked it in 1465. That was the day, the year, and it comes in this time when it goes off again. So let's just see what it is that he says. Regiomontanus says that he observed Mars slightly north of a straight line through the first and second star of Sagittarius, 1.5 times this distance. So that's how he describes this. Then he also says that according to the tables, Mars should be at 6 degrees of Capricorn, which I reckon is over here. But he doesn't say what position he gets numerically for Mars, and he doesn't say that there's something like a 5-degree discrepancy going on here. 4 or 5, something like that. Now, what's the problem? There is no coordinate grid sitting in the sky where you can make that measurement. So how can you know where Mars is? You can know where Mars is only if you know where some of these stars are. But you don't know for sure where the stars are because of precession. And as I said, Ptolemy had really botched it on figuring out precession, because his position worked out that between his time and Hipparchus's time, the precession had been chugging along at 1 degree per 100 years. And in fact, it's 1 degree in 71 or 72 years. So that between Hipparchus and Ptolemy, it added up to a degree error. And then the question was, for astronomers like Copernicus and so on, do you want to throw away the observations from Hipparchus, or do you want to throw away the ones from Ptolemy? These are precious things. You can't go back and duplicate them. You've got to set your precession in some strange way so that it'll work at 100 at a degree per century for that distance of nearly 3 centuries between the two astronomers, and then have it speed up after this. And you do that by adding another circle, which is called trepidation, which works for a while, but by the time of Copernicus, it was getting really off. It no longer could give you right results. And Regiomontanus is so busy, he's learning Greek so that he can translate the Almagest. He's set up as a printer. He's the first scientific printer. He's so busy doing all these things that he doesn't really have time to go out and try to get the precession fixed. So he doesn't know. So there it is. It's sitting there like a time bomb in the observations, but nothing really calling your attention to it. And by the way, that observation is reprinted in this big book. So it was there. Let's go back to these observations, and it's interesting to see that there are conjunctions with Regulus, which is a star that lies close to the ecliptic, and therefore it can get close enough that if you could get a position of Regulus, you could then use that as a reference point to get the actual positions of the planets. And Ibn Yunus got a very accurate position for Regulus. I'm not sure how he did it, but it was one of the most accurate numbers coming out of the Islamic period. But the observations that he gives for the conjunctions of Mars and Regulus are really quite inconsistent, more than a degree in error on a couple of them. So it wasn't really quite enough to pin down the system, but at least they had a feeling of what they were trying to do. So that's why here with Al-Kawashi's measurements, 2 of them are with Regulus. It is a way of getting a handle on the tables. But if you wanted to have an epicycle on the epicycle, you're going to need a lot of observations. And to just have 3 observations of Mars, which would be enough to check on Ptolemy's eccentricity and so on, it would not be enough to allow you to go another step to add another epicycle in it. So, I played around with this diagram some. I thought maybe it was because there were bad parameters going into the orbit of Mars, and I fiddled around with the parameters and found that even if you put the best modern numbers in, it still does this. So let's see why. Kepler approached it in a different way, not to try to figure out what was going wrong with Mars, but what he did solved the problem anyway. What he did was to say, there's got to be some physics in all of this. Why are the planets going around faster when they're closer to the Sun and much slower when they're out there by Saturn? It must be that there is some power in the Sun that is driving the planets. And the closer you are, the faster they go. How can it be that in the Copernican system, the Earth is going around at a constant rate? Because sometimes it's closer to the Sun and sometimes it's farther. Surely the Earth should be going faster when it's closer to the Sun. And how do you fix that? Well, you have to fix that by moving the orbit of the Earth so that it can have an equant. In other words, you want to cut the eccentricity in half. And now Kepler has a very clever way to figure out where the Earth's orbit is. He takes a particular position of Mars in its orbit, and he observes it from this spot. Rather, he finds the observations in Tycho's big book. And then, as Mars slowly gets all the way around and back to this point, the Earth goes around once and a little bit more than twice, and is in a new position here. And now you let that repeatedly happen, and it gives you these 5 positions of the Earth with respect to Mars. And it's enough leverage to show that the Earth's orbit needs to be slipped to move so that it has an equant point. And now let's see what that does for you when you're looking at Mars. Here is Mars at its closest point. It's at its perihelion, and the Earth is at aphelion, so that it brings them together in the closest possible way. But now, if you have to slide the Earth's orbit, it changes the direction that you're looking. And you recompute it this way, and lo and behold, that glitch of 5 degrees disappears. So, Kepler's greatest achievement in getting the planetary theory working is fixing the Earth's orbit, not getting an ellipse. He gets like a 10% improvement, and then he gets another one, which would mean from the beginning just a 1% improvement for having the ellipse. But that's how it works. So, what is the general conclusion? It's not just that there weren't epicycles on epicycles, but it was that during that whole millennium and a half, there simply were not the observations being made that could have pointed out how inaccurate Ptolemy was. It was too hard to do that. And there's just no evidence that observations were being made on a scale that could have found that. So, this is part of the mythology. More and more of these epicycles were added by Ptolemy's medieval successors as they sought for ever greater accuracy. I'm sure they would have liked to have greater accuracy, but it's not evident that they were busily searching for ever greater accuracy. So that is my indictment of modern writers. For example, the 1970 Encyclopedia Britannica, which said that by the time of Alfonso, 40 epicycles were required for each planet. I wrote to them and asked them, where did that come from? And they said, the author of the article is no longer living. So this, I hope, gives you some admiration for some of those workers in times past, but also some appreciation for what really wasn't happening.
We have questions?
I had been looking for a long time to find out when the epicycles-on-epicycles myth began. I knew it was fairly common in the second half of the 19th century, but now this particular quotation from John Herschel is the earliest one that I know about.
But you referred to Milton.
Milton said epicycle on cycle, orb on orb, and I have no idea where that came from, but it wasn't very explicit.
Was the context even astronomical?
Only slightly. It's part of Paradise Lost.
You said that the greatest achievement of Kepler was to, the shift that allowed that fixed the observation of Mars by shifting Earth's orbit a little bit. Wouldn't you rather say that? I would argue that his greatest achievement was actually the Kepler's laws of motion and the fact that he did discover the ellipticity of orbit, or that there are ellipses, and that allowed them to develop into physics. These three laws can translate directly to Newton's laws, essentially.
Yeah, I think you're on the right track there. I think his greatest achievement was not the ellipse, but his greatest achievement was insisting that there should be physics behind the explanation. So, yes, it's part of that theme. But he was really unusual in that day. His teacher, Michael Meslin, said, you should forget about all this physics stuff. That's not what an astronomer is supposed to do. Wait a minute. You're first.
Yes. Do we know what motivated Tycho to get into this big data? It was so much better than it had gone before, and I believe it was more accurate too. Do we know why he cared?
He was, as a young person, already getting interested in astronomy, and he was very shocked when he discovered that the great conjunction between Jupiter and Saturn, which happens every 20 years, was wrong by about 3 degrees, he says, 3 days in the Copernican tables, and when he checked it in the Alphonsine tables, it was 30 days wrong. Now, that was just an accident that at that particular time the Copernican tables were so much better in that instance, because as he later found out, the Copernican tables could sometimes be worse than the Alphonsine tables. But at any rate, that set him on fire, and he did that. He was still a teenager when he saw that, and he decided he would devote his life to trying to get better observations so it could be straightened out. And as a member of the nobility, he had access to lots of funding, and he said that it cost more than a ton of gold to supported his observatory. Now, I once calculated it, and this was a couple of decades ago, that the Smithsonian was at that time costing 3 tons of gold per year.
There were a few more people.
Per person, I suppose, it was more efficient.
Yeah. Well, that was pretty close to my question, but I wanted to know about the conjunctions. The observations are much easier if you just look at conjunctions. Is that what was going on before Tycho? Because Tycho had instrumentation, even though it wasn't telescopic.
Copernicus, for example, lists conjunctions in one of the very few manuscript scraps that comes up, and he then realized that Jupiter was okay, but both Mars and Saturn were wrong in the tables, but that never recurs in any of his writings, and he doesn't show that his tables would have predicted it better at that point. But you're absolutely right that the conjunctions don't require fancy instrumentation. You just have to watch and wait.
Owen, was Newton aware of Kepler's physics, quote unquote, in the way you described it, where Kepler thought surely the sun must be, how did you put it, exerting influence on the planet?
I don't think that Newton got much of Kepler from reading the Astronomy and Nova directly. He got the 3 laws through secondary sources of people who cited them. And by the way, Kepler never called those out as being laws. They were numbered and addressed as laws more than a century later by one of the French astronomers, Lalande.
I wondered whether Newton's whole postulate of gravity had any heritage in Kepler's speculation.
He certainly used Kepler's material, but Newton was fairly arrogant about it. He said Kepler guessed that it was an eclipse, but I proved it.
Any more questions?
Oh, okay.
I'm just wondering, what was the duration of which the uncertainty was visible? Days or weeks?
A few weeks, yeah.
So it's easily possible that it could be easily considered better.
Yeah, but not every time.
People somehow need to get this supernova.
Okay, so are there more questions? All right, let's thank Owen again.